Hello everybody. So, in the last class while discussing the properties of the thermodynamic potentials, we came across, or rather we developed a set of Maxwell's equations which I have written down or which have been written down here for your convenience. Now, if you observe this particular set of Maxwell's equations, you find that these equations, they actually relate the change in entropy with the change in pressure, change in volume. So, in other words, this basically relates the changes in entropy with changes in pressure volume, and we will also see how they are related to the changes in temperature. And from here we are going to derive the changes of enthalpy, internal energy, etc., with changes of pressure, volume, etc., and this is as an endeavor to relate the measurable and the non-measurable properties, so that we can estimate the non-measurable properties simply by measurement of the measurable properties. Now, among the measurable properties, the common ones, as we all know, they are pressure, volume, temperature, out of which pressure and temperature are most easily measured and most easily controlled. Along with that, we also know that beta and kappa, these two the coefficient of isothermal compressibility and the coefficient of thermal expansivity, these two can also be measured. Now, let us see how we can play with this set of Maxwell's equation in order to find out, say, the change of entropy, the isochoric change of entropy with pressure. What does isochoric change in entropy means? It basically means del S del P at constant V, right. Now, if we observe, then this is related to, if you see the first Maxwell's equation, this will be equal to del V del T at constant S. So, therefore, we can write it down as, say, for instance, S from some particular initial state, say P2 V1 to say V1 P1, this will be equal to del S del P at constant V integral of, say, from P1 to P2 dP, which can also be written down as minus integral P1 to P2 del V del T at constant S dP. Right. In the same way, suppose I tell you to find out the change, the isobaric change in entropy with volume. What does this signify? This basically refers to del S del V at constant P, right. So, therefore, we would like to find out integral of this as a function of volume, that means it is from V1 to V2, this is dV. Okay. So, therefore, this is equal to S say P1 V2 minus S P1 V1, which will be equal to, if we relate it, we find that in this particular case the relevant Maxwell's equation is the second Maxwell's equation, isn't it? We find out that the second Maxwell's equation relates del S del V at constant P with del P del T at constant S. So, therefore, this will be equal to integral V1 to V2 del P del T at constant S dV, right. In the same way, suppose I would like to find out the isochoric change in temperature. What does that mean? That means del S del T at constant V. Now, can you tell me in what way can I find this particular quantity out? Can I not write down this quantity as del U del T at constant V divided by del U del S at constant V? What is del U del T at constant V? We have already discussed the specific heat capacities as quite constant volume and constant temperature. What is del U del S at constant V? Remember the differential equation du equals to T ds minus P dV. From there we find del U del S at constant V is nothing but equal to the absolute temperature, right. Same way, if you want to find out del S del T at constant P, we can simply write it down as del H del T at constant P divided by del H del S at constant P. All these things, they come from the cyclic rules. Again we know del H del T at constant P is nothing but equal to del Q del T at constant P, which was equal to Cp, and this term again from the original dH equals to T ds plus V dP, we get this is equals to T. So therefore we find that in this particular way we have been able to relate the change in entropy with change in pressure, with change in volume, with change in temperature at constant volume, with change in temperature at constant pressure. Now before I proceed, I would like to remind you that when we were discussing the Maxwell's equation or the evolution of Maxwell's equations from the thermodynamic potentials, we had derived the equations in terms of total quantities, and I had used all sorts of capital alphabets in order to denote V, S, G, A, U and H. Now as I told you that all of these are extensive properties, and the same relationships which hold for total properties are also applicable for molar properties or for specific properties. At this moment we are going to deal with molar properties, and therefore since we are dealing with molar properties, I have written all these Maxwell's equations in terms of lowercase alphabets, meaning that I have been relating the change in molar entropy with the change in molar volume, pressure and temperature. It is important for you to remember that the same equations that I have derived here can be derived for total quantities as well. The important thing to remember is, if you are dealing with total quantities, all the quantities here should be total. If you are dealing with molar quantities, all the quantities written down is molar. That is the only thing that we need to remember. Well, now suppose we go for the, suppose in this particular case, now let us see, once we have derived, or rather once we have discussed how entropy changes with pressure, volume, temperature, etc., then we should be in a position to derive the TdS equations which are known, or in other words, we should be able to derive entropy as a function of volume and temperature, and entropy as a function of pressure and temperature. Let us see how we go about doing this. In order to derive this in terms of volume and temperature, we just need to write this as ds equals to, as a function of temperature and volume. So this is del S del T at constant V dt plus del S del V at constant T dV. In the last slide, I have already derived, this is nothing but equal to Cv by T dt plus del P del T at constant V dV. The Maxwell's equations have been written on the side so that you can refer to them and find out the way I have derived. This can also be written down in terms of beta and kappa. In that particular case, this becomes Cv dt plus beta by kappa dV, right? And using the, and if in case we would like to find entropy in terms of temperature and volume, then in this particular case again we write it down in terms of temperature and pressure. Sorry, I think I had mentioned volume, it was pressure. So I can write it down in terms of temperature and pressure, and in this particular case this becomes Cp by T dt minus del V del T at constant P dP, which can also be written down as Cp by T dt minus V beta dP. Right. Now, usually what we do is, these particular equations, they are written in the form of TdS for our convenience, right, and we usually write them down as TdS equals to Cp dt minus T of this, or in other words, here also we would like to write it down as Cp dt T of this, right. Here also, suppose I would like to express it in terms of your TdS equations, then in that case the equation can be written down as, it can be written down in the form of TdS equals to Cv dt plus T of beta by k kappa. Now, these two equations, they not only show us how S varies with temperature, volume and pressure temperature, pressure and volume temperature, but they can also be used for finding out a large number of other things as well. For example, let us see, for example, suppose we would like to find out u as a function of t and v. How to proceed in this particular case? We already know the basic equation. What is the basic equation that we know? We know that du, I would just like to make the pen a little more thicker so that it is easier for you to see. We already know du, that is equal to Tds minus Pdv. It has become a little more, just make it little, yeah. This we know, and from the first TdS equation which I have written down, from this particular TdS equation, can I not substitute this particular TdS and write it down as Cv dt plus T del P del T at constant V minus P dV, right? Or in other words, I can also write it down in the terms of beta, kappa, etc., etc. I can also write it down as Cv dt plus T beta by kappa minus P, sorry, this is dV. I have made a mistake. This is going to be dV, sorry, right. So, therefore, by using the two TdS equations, the first TdS equation, I could actually express u as a function of Cv dt in this particular equation. Okay. Now, from here let us see some very interesting results that we get. Say for example, for an ideal gas. For an ideal gas, what do we get? For an ideal gas, what is del H? Suppose from here, sorry, not del H, what is del U, del V at constant P? We know for an ideal gas PV equals to RT for 1 mole, since we are dealing with molar properties. So, therefore, in this particular case, if you substitute del P del T at constant V, then for an ideal gas, this particular term it becomes R by V. So, RT by V is nothing but equal to P. So, therefore, what do we find? The volume dependence, the internal energy dependence on volume for an ideal gas, it disappears off, and we find that del U del V at constant T, that becomes equal to 0, right. And I think I would like to remind you that when we were dealing with the first and second laws, under that condition I had told you that for an ideal gas du equals to Cv dt. You had assumed that what I was telling was correct. I could not prove that at that time. Now, I show you from Maxwell's equation why for an ideal gas del U del V at constant T equals to 0. Same in the similar way, suppose I would like to find del U del P at constant T. How to find this particular term out? We know from the cyclic relationships del U del P at constant T, del P del V at constant T, that will be equal to del U del V at constant T, isn't it? From the cyclic relationships, we have already proved that this is equal to 0. We know that this term is not equal to 0. So, therefore, what does it imply? It implies del U del P at constant T will be equal to 0, right. So, therefore, we have not only deduced du in terms of Cv dt, but we have also shown that for an ideal gas U is independent of pressure and volume, it is just a function of temperature and nothing else, which is a very well known equation. In the same way, suppose I would like to derive the equation for, in the same way, if I would like to derive the equation for HTP, right. In that particular case, what do we get? For HTP, suppose I, in the same way, in this particular case, I would again like to remember that, sorry, dH equals to, again from the TdS equation, dds minus Vdp, right. Again I substitute the second TdS equation here the same way that I had done, and then from there once I substitute, what do I get? I get dH is nothing but equal to Cp dt plus V minus T del V del T at constant P dP, or in other words this can also be written in terms of beta kappa etc. We can write it down as Cp dt plus V into 1 minus beta T into dP, right. So, therefore, and this particular equation is particularly important because for most of the practical applications we come across enthalpy changes of physical as well as chemical processes. In this case also, suppose I try to find out del H del P at constant T for an ideal gas, what do I get? Suppose I do it for an ideal gas. So, therefore, for an ideal gas, let me find out del V del T at constant P. What is del V del T at constant P for an ideal gas? It is nothing but equal to R by P. So, therefore, RT by P for 1 mole of the gas is nothing but the molar volume. Therefore, this whole term cancels out if we are dealing with ideal gas, which shows us that del H del P at constant T for an ideal gas is 0. Just the way we had proceeded for internal energy, we can show in this particular case del H del V at constant T will also be equal to 0. I will just write it down properly. So, this is also equal to 0. So, therefore, for an ideal gas, what do we know? H, it is a function of temperature only, H ideal. We denote ideal gases with a subscript 0. So, therefore, from here we can write H 0 is nothing but equal to T1 to T2 Cp 0 dt. At this juncture, I would just like to remind you once more something which I had mentioned in the last class, something about nomenclatures. By this time, you must already have been aware of the fact that we are dealing with a large number of properties, and if we do not denote the properties consistently, we might get lost in it. So, therefore, again I would like to remind the consistent nomenclatures that we are going to follow in this class. All the total properties, the total energy, the total entropy, the total enthalpy etc., all of them will be denoted by capital letters. All molar quantities will be denoted by lowercase letters, and you must have noticed from the beginning of the class I am just using lowercase letters just to emphasize upon you that I am dealing with molar properties only, but at the same time it is important for you to remember that the same equations that I am deriving will be applicable for total properties as well. Now, I have introduced one more additional nomenclature. What is it? Whenever I am dealing with ideal gases, I am just putting a superscript 0 just to differentiate that these properties refer to ideal gases in contrast to any particular real gas or any particular real substance, right. Now, so by this particular time, we have already come across we have deduced the two TdS equations. From the two TdS equations, we have also derived we have also derived equations for dH and du. Now, and we have also derived, or we have also shown that both enthalpy and internal energy for an ideal gas, both of them they are unique functions of temperature and both of them are independent of pressure as well as of volume. Right. Now, before I proceed further, I would like to ask one particular question to you. We have this particular equation. At this juncture, I would like to remind you that for most of the situations, we will be dealing with changes in enthalpy and entropy as we come across changes of these quantities in practical applications. So, primarily I will be dealing with dH, ds quantities, but it is important for you to keep in mind that we can proceed similarly for du as well. Right. Suppose I have some particular gas at a pressure P1 and a temperature T1. I would like to take it to another state with pressure P2, temperature T2. Now, how do I propose to proceed? Suppose I would like to plot the changes on a PT curve, right. So, here what do I have? I have one particular gas at P1, T1, right. I would like to take it to P2, T2 state. What are the different ways by which I can perform this particular process? One is I can perform an isobaric process initially, okay, where I go from P1, T1 to P1, T2 and then I follow an isothermal process. This I can definitely do. For this particular process, initially I have performed an the initial process was isobaric. So, for this particular process, I can write this down as del H del P dP. This has to be evaluated at T equals to T1. This integration will be from P1 to P2 plus del H del T at dT, this is at constant pressure, this is at P equals to P2 and this integration is going to be from T1 to T2. This is one particular thing that I can do. What have I done for this particular path? Initially, I have performed an isothermal compression from P1 to P2 at temperature T1 and then I have performed an isobaric heating from T1 to T2 at pressure P2, right. On the contrary, there is one other thing that I can do in this particular case. I can first perform the isothermal process and then I can perform the isobaric process. Very well, since at both these points I am dealing with properties which are dependent on the initial and final states as we already know. So, hardly it should matter in this case. For this particular case, what is my H2 minus H1 equals to? In this particular case, initially I am going to write T1 to T2 del H del T at constant P equals to P1 into dt plus integral P1 to P2 del H del P at constant T equals to T2 dP, right. So, therefore, I can either perform it by this process or I can perform it by this process. Normally, it should hardly matter, okay. But let us see from the practical point of view which particular process we should be or rather we should be opting for. Now, tell me what is del H del P at P equals to P1. This should be something like, this should refer to Cp at P1 which should be equal to del H del T at P equals to P1. And for this particular case, what do I need? For this particular case, I need Cp, I need information on Cp at P2. And in order to find these two properties, what do I need? I just need, if you would recollect, I simply need the PVT behavior of the gases, and this I need for, sorry, I have made a mistake in this particular case. This is not here. For this case I will be needing this one is equal to Cp at P2, sorry. So, therefore, we find in order to find this particular integration and this particular integration, for these two integrations I just need the PVT behavior of gases, right. I need to find out how H varies with P at T1. For this case I need to find out how H varies with P at T2, right. But from the practical point of view, we know that Cp data are available for ideal gases only. Cp data are not available for, or rather they are much more rare and much less accurate for higher pressures, right. So, therefore, usually at low pressure Cp data are available. So, therefore, from practical considerations we would neither prefer this particular process nor we would prefer this particular process. From practical considerations, what are we going to prefer? We are going to prefer, I will select a separate color for your convenience. We shall be preferring, we would like to come down to pressure P equals to 0. Then at P equals to 0, we would like to perform the change in temperature, and then from here we would like to go to P2 T2. So, the process which we would be preferring in this particular case, that particular process is we would prefer to undergo an isothermal expansion of the gas from P1 T1 to P equals to 0. At this P equals to 0, where the gas behaves as an ideal gas, we would like to bring about the change in temperature. And then once the change in temperature is affected at the low pressure, then from this P equals to 0, we would like to go to P2 T2, right. So, this is the practical path which we are going to adopt. We neither adopt this path nor we adopt this path. Also, normally just we would have felt that it hardly matters, we can take up any path, but normally, but under practical considerations we would prefer this path. So, for this path, suppose I would like to write down H2 minus H1 for this particular path equals to. Let us see what should be the H2 minus H1 for this particular path. For this particular path, it is going to be, sorry, for this particular path, the H2 minus H1 expression, that should be equal to, it should comprise of an isothermal expansion. So, it is P equals to P1 to P equals to 0. This del H del P at constant T dP plus at this particular pressure at this P equals to 0, we would like to perform del H del T at constant P from T1 to T2 at P equals to 0 dt plus from P equals to 0 to P equals to P2, we would like to perform del H del P at constant T dP, isn't it? So, therefore, this would be at T2, this would be at T1, and we know the value of this now. This is nothing but equal to integral T1 T2 Cp0 dt, and we all of us know that Cp is a unique function of dt. Normally, Cp0 is given by a plus bt plus ct square plus so on and so forth. So, therefore, we can find out Cp0 as a function of t, and we can use that data for due to which we had devised the roundabout path in bringing about the change of this state from P1 T1 to P2 T2. So, now if I complete this particular equation, so what do I get? I find that this will be equal to, this will amount, this is nothing but equals to V minus T del V del T at constant P, this whole thing integral P equals to P1 to P equals to P almost 0 dP, and this particular part that also comprises to the same term del V del T at constant P dP, but in this case this is from P equals to 0 to P equals to Pt. This here we are supposed to evaluate it at T2, here we are supposed to evaluate it at T1, right. So, therefore, for this particular case what we have done actually, this particular case we have devised a path in order to use Cp0, and other than the data on Cp0 we find that we just need data on the PVT behavior of gases, which tell us how volume is going to vary with temperature at a constant pressure. Once we have an idea regarding the PVT behavior of the gases, we are able to calculate these two terms, and we can find out H2 minus H1 for any change of state from any initial state T1 P1 to any final state T2 P2. We continue with our discussions in the next class on this particular thermodynamic estimation of properties. Have a good day.